Is Dickens, and we are talking about salts. And in today's lesson, we want to discuss how you can obtain crystals from any given salt solution. So we started that by obtaining the solution itself, and we shall use copper sulfate as our example. So we are talking about obtaining crystals from a solution. The one we are going to consider is copper sulfate. So our subheading under this is obtaining copper sulfate crystals. Obtaining a copper sulfate crystal. So let us start by preparing the copper sulfate solution first, and then from there we shall see how we can now get the crystals from the solution itself. So the procedure is as follows. So first, number one, you place about 20 centimeters cubed of water in a beaker. So you just measure that one using a measuring cylinder. Then number two, you add a spatula full of copper sulfate. We want to prepare the solution first, then from the solution we shall obtain the crystals. So you add a spatula full of copper sulfate to the beaker as you stir. So we are simply stirring to make sure that the solid crystals that we are having are able to dissolve in the water. Thirdly, continue adding copper sulfate crystals until no more can dissolve. You'll realize at one point when you add more and more copper sulfate, none of it will dissolve. So we are saying the point at which no more crystals are able to dissolve, we are saying that that solution has reached a point of saturation. So such a solution, we are going to call it a saturated solution, one in which no more solute can dissolve. Then after that, you decant the resulting solution. Decant the resulting solution onto an evaporating basin or evaporating dish, and then from there you heat the solution until it is about to form crystals. So how will you know? How will you be able to tell that the solution is now ready to form crystals? We do that by using a glass rod. So we shall take a glass rod and then you dip into that saturated solution, and then you hold it in the air, and then you observe the glass rod. When you see crystals on the glass rod, after allowing it to cool, it will mean the solution is ready to form crystals. So if it is ready to form crystals, you now stop heating and allow it to cool. So that brings us to the next point in our procedure. You allow the saturated solution to cool. We have said you are allowing it to cool after confirming that it is ready to form crystals. And we have said, how do you tell that it is ready to form crystals? By dipping a glass rod into that solution and holding it in the air. Once the glass rod has cooled, the solution, you'll be able to see crystals on the glass rod, and for that case, you'll now stop heating. And then, lastly, is you dry the crystals formed using or between filter papers. So we shall see why we are using filter papers to dry the crystals formed. So this is how our apparatus will look like. So remember, we are heating the saturated solution. So this is how we are going to heat it. We are going to heat it using a water bath. So as shown here, so we shall have our beaker. This beaker contains some water in it. So remember, we heat using a water bath, and we have to put our tripod stand here, and then below it we put our source of heat. So this will be our source of heat. That's our heat. So heating shall be done here. Then on top of our beaker, so this is our beaker. This will be our beaker. So remember, the beaker contains some water. So here we have water. Then on top of the beaker, we shall put our evaporating dish. So the evaporating dish will be here on top of our beaker, and that's where we shall put our salt solution, that is copper sulfate. So we shall put our copper sulfate solution here. Remember, from it we are supposed to obtain the copper sulfate crystals. So this is our evaporating dish. And then this is our copper sulfate solution. So that's how we arrange the apparatus for heating our saturated solution. Remember, we have said while heating, you'll be required to dip a clean glass rod into this salt solution so that you're able to find out when it's ready to form crystals. And we have said, how do you know that? Once you remove the glass rod from this solution and then you hold it in the air, it will cool. On cooling, you'll be able to see some crystals on the glass rod. That will mean the solution is ready to form crystals. If it is not ready to form crystals, then you'll continue heating. So that's how we shall arrange our apparatus. So we have said, after that, you will be able to remove the evaporating dish from the source of heat, and then you put it somewhere, allow that solution to cool. After cooling, the solution will form crystals, and those crystals that we shall obtain will be the crystals of copper 2 sulfate. So we have mentioned the word crystals. It's good you also know the definition or the meaning of the word crystals. Remember, we are obtaining crystals from a solution of copper sulfate. So therefore we are saying crystals can be defined as what? So we are saying crystals are simply the solid particles obtained when a saturated salt solution cools. So we are saying after copper sulfate solution will cool, it will form copper sulfate crystals. So that's how we get the meaning that crystals are obtained from a saturated solution. We also have this word saturated solution. Let's also define it. Saturated solution. So remember, in our procedure there is somewhere we mentioned and said you add copper sulfate, continue adding until no more can dissolve. So at that point where no more copper sulfate can dissolve, we say such a solution is saturated. So what is it? So it means a solution in which no more solute can dissolve. No more solute can dissolve at a given temperature. Of course, we know a solute from Form 1. A solute is any substance that dissolves in a solvent, whereas a solvent is a substance that dissolves a solid. So in this case, our solvent is water and our solute is copper sulfate crystals. Now, the whole process of formation of crystals, we are calling it crystallization. So we have another term here, crystallization. Crystallization is simply a process in which crystals are formed when a saturated solution cools. So the process, we call it crystallization, and the solid particles formed are called crystals. So you'll realize that we are talking about crystals. For crystals to be formed, then it means there must be some water that must be present in that any given salt. So a salt can either be in form of crystals or in powder form. Those salts which are in powder form, we say they don't have water of crystallization. But those salts which are in form of crystals, we say they contain water of crystallization. So let's also define that word, water of crystallization. Water of crystallization. So water of crystallization is simply water that is incorporated within the structure of a salt. So anytime you're talking about crystals, then it means that given salt contains water of crystallization. So we are saying water of crystallization is important in the formation of crystals for any given salt. So learner, we have said this, that we can obtain crystals from any salt solution by simply carrying out evaporation, as you can see from the diagram there. And we have said as you heat, you are supposed to dip a glass rod in that given salt solution to find out when it's ready to form crystals. After that, you remove it from the source of heating and then you allow the salt solution to cool. On cooling, it will form some solid particles, and those solid particles formed are called crystals, and the process of formation of crystals is called crystallization. And that is the end of our lesson. I want you to try these questions during your own time. So try these questions. I want you to try these questions here. So our first question is define term saturated solution. Define the term saturated solution. Secondly, define the term water of crystallization. Water of crystallization, and state its importance. Why is water of crystallization important? Thirdly, I want you to try and answer why crystals cannot be dried by heating. Why you cannot dry the crystals by heating? Remember, we have said any salt, for it to have crystals, then it means it contains water of crystallization. So you can get the clue from the definition of water of crystallization. Then fourth question is explain why the solution is not evaporated to dryness. So you try those 4 questions, and I believe you shall be able to handle any question pertaining formation of crystals. So that's the end of our lesson for today. I'll see you in our next lesson. Thank you.
Welcome to our physics lesson today. My name is Purity Anzelimo, and our topic of today is quantity of heat in book 3. So in our lesson today, we continue with the quantity of heat as our topic, and we move on from where we left during our previous lesson. Now, during our previous lesson, we looked at the specific heat capacity, denoted by a small letter C. And we said that specific heat capacity simply refers to the amount of heat required to raise the temperature of a unit mass of a substance by 1 Kelvin. And therefore we say that specific heat capacity is given by the quantity of heat divided by the mass of the substance multiplied by the change in temperature. So make note of this, and from this therefore we can say that quantity of heat, when we cross multiply, quantity of heat will therefore be equal to mass multiplied by the specific heat capacity multiplied by the change in temperature. So we are going to make use of that formula. Make note of it. So quantity of heat is mass times specific heat capacity multiplied by the change in temperature from the definition of specific heat capacity. Now, before we look at the continuation on the specific heat capacity, where we are going now to look at the determination of specific heat capacity using different methods, and in our case today we look at, in this lesson we look at the method of mixtures. But before that, I would like you to note the following. NB. Now, if we have 2 substances which have the same mass and they are being heated by the same amount of heat, Now, we'll have them having different change in temperature. You need to note that. For example, if we have a substance like a metal like iron, and maybe we have another substance, for example, we can talk of copper. Now, when these two, let's say they are of the same mass, let's say the mass of iron that we are heating is maybe 10 kilograms. And also the mass of copper that we are heating, let's say, is also 10 kilograms. When we subject it to the same amount of heat, they acquire different temperature changes. And this is because they have different heat capacities. So I want you to note that. So we are saying that, that if two substances So I want you to note that if two substances of the same mass are subjected to the same amount of heat, let's say we are heating them using a certain amount of heat, for example, 1000 joules. We are saying that they will have different temperature changes due to their different specific heat capacities. Hopes that is clear, because these two substances have different heat capacities, and therefore, even if we subject them to the same amount of heat, they will going to experience different temperature changes. For example, if we talk of inchi iron, whose specific heat capacity is 460 iron, whose specific. Now we are taking an example of iron whose specific heat capacity is 460 joules per kilogram per Kelvin. So we are saying that when we supply heat of 416 joules to a unit mass of iron, the temperature change will be 1 Kelvin. So make note of that. So iron whose specific heat capacity is 460 joules per kilogram per Kelvin this means that when we supply heat to 1 kilogram of iron, it means that it will give in or out 460 joules. That is the heat in 1 Kelvin. That is a temperature change of 1 Kelvin. So we can say that 1 kilogram of iron would give out or in 460 joules of heat when the temperature changes by 1 Kelvin. So we can say the following, that because we have 460 joules per Kelvin joules per kilogram per Kelvin, then it means that 1 kilogram of iron will therefore take in or out. So make note of that when we are saying that the specific heat capacity is 416 joules per kilogram per Kelvin, it means that 1 kilogram of iron will take in or out 416 joules of heat when temperature changes by 1 Kelvin. And this qualifies what we are saying, that when two substances of the same mass are subjected to the same amount of heat, they are going to have different temperature changes due to their different specific heat capacities. So if we have another metal, for example copper, the specific heat capacity will be different. So meaning that in this case, for example, where we are saying 1 kilogram of iron taking in or out 416 joules. So in case maybe we have another substance or another material, then it is going to take in or out a different amount of energy depending with the specific heat capacity. So 1 kilogram of iron from this will take in or out 416 joules of heat when temperature changes by 1 Kelvin. Hoping that that is well understood, you can be turned to explain what that means. So during our lesson, now we want to look at how we can determine the specific heat capacities. So we want to look at methods of determining specific heat capacities. Methods of determining specific heat capacities for different substances. So methods of determining specific heat capacities, and in this we'll now will be able to I'll explain an experiment that we can use to determine the specific heat capacities of different materials. So by the end of this lesson, you should be in a position to explain that experiment and then also be able to calculate the specific heat capacity. So I want us to start with the method of mixtures. We start with the method of mixtures. Now, in the method of mixtures, here we want to mix a relatively hot substance with a relatively cold substance. So when we mix them, we know that there is going to be flow of heat until the two substances, or they can even be three, until the two substances acquire what we call a thermal equilibrium, whereby both of them will have the same temperature. I can give you a good example. Let's say you have some hot tea in one cup, and you have very hot tea from your Mekol. You have very hot tea in one cup, and you have very cold tea in another cup. Let's say the hot tea is at 90 degrees Celsius, for example, at 90 degrees Celsius, and then the cold one, let's say, is at 25 degrees Celsius. Now you want to mix the two, the 1 cup of hot tea and the other cold tea. So when you want to mix them, you want to mix the two. So what will happen as you mix? The hot tea will be losing heat to the cold one, and the cold one will be absorbing heat from the hot one. So at long last, you will find that the hot one becomes, or when you mix the two, this temperature will lower, and this one will increase to a certain steady temperature. Let's say a temperature of like 55 degrees Celsius. So that is what we are talking about. So there will be flow of heat from this hot tea to the cold tea. So the cold tea will be absorbing the heat as the hot one loses. And it will come a time whereby the tea will be at a uniform temperature. So that is at 55 degrees Celsius. So this is for two substances which are the same. We can have substances which are different. For example, when you are having water and a hot metal, water at maybe room temperature and a hot metal, let's say at 100 degrees Celsius. So when the hot metal is dipped into the cold water or the water at room temperature, it's going to lose heat, whereas the water gains heat. So it will come a time whereby now the two will attain a certain temperature, which we are calling a steady temperature, which will be equal. And that state is what we refer to as thermal equilibrium. So we can explain the following before we go to that experiment on determination of the specific heat capacity using the method of mixtures. So when we mix a relatively hot substance with a relatively cold substance, energy will be transformed from the hot body to the cold one until thermal equilibrium will be established. So on mixing, so we are saying on mixing a relatively hot substance with a relatively cold substance, heat flows from the hot body or from the hot substance to the cold one until thermal equilibrium is established. So at thermal equilibrium, there is no net heat flow because the two substances will have achieved the same temperature, and therefore if we hand the hot metal and the cold water, if both of them now achieve a steady temperature, let's say of 50 degrees Celsius, then it means that there will be no net heat flow, and therefore we say that thermal equilibrium has been achieved. So we want to move ahead and explain on that experiment that we can use to determine the specific heat capacities of different substances. Now in the method of mixtures, majorly we are going to use an instrument we refer to as a calorimeter. So we are going to use a calorimeter which will help us in the method of mixtures, and I'll be explaining why we use a calorimeter and what is a calorimeter. So we can look at the precautions to minimize. So in this we use a calorimeter. Calorimeter is used in the method of mixtures in the determination of the specific heat capacity. Now, we need to know the following about the calorimeter, that the calorimeter should be number one, that calorimeter or that instrument that we are using, which we are going to have a diagram for, should be number one, highly polished. Now we learned that in heat transfer book 2 that the shiny surfaces are poor emitters of heat. So when we use a highly polished calorimeter, it's to minimize heat loss to the surrounding. So all this that we are having here, the highly polished calorimeter, we are saying is to minimize. This is to minimize heat loss to the surrounding. Make note of that. Then again, the calorimeter number 2 should be heavily lagged. Heavily lagged. We also learned about lagging in heat transfer, where we say that lagging is covering the good conductors of heat with insulators to minimize heat loss. So it is again heavily lagged, again to minimize heat loss. So this one is also to minimize heat loss. And finally, the calorimeter should have, in this case now, the calorimeter should be highly polished, should be heavily lagged, and should have a lint which is a poor conductor of heat. So we can say that it should have a lint. We can talk of an insulator lint. That is a poor conductor of heat. So again, the reason as to why it should have a lint which is a poor conductor of heat is again to minimize heat loss. So this one is again to minimize on heat loss. And that's why we go for the calorimeter, because the calorimeter can be used to minimize heat loss when we are conducting the experiment or this practical on the method of mixtures, because it has the following features. It is highly polished, it is heavily lacked, and it has an insulating lint. So this is how our calorimeter looks like. And this is what we refer to as a calorimeter. It's not a complex instrument. So this is what we have as our calorimeter. It can be a copper calorimeter. It can also be made of aluminum, like mostly the ones we use in the laboratories. The school lamps are made of aluminum. So here we are saying this is now our lagging material. This is the lagging material to minimize the heat loss. So this is the highly polished. We are saying that the calorimeter is highly polished. So this is a highly polished surface. This one is highly polished. Then we are saying that it has a lint. It has a lint. This is the lint, and the lint has two openings, one for inserting the thermometer. This is our thermometer. And two, the lint has an opening also for what we refer to as a stirrer. It is used to stir the content. So this is our thermometer. And this is what we are referring to as our stirrer. So that is what we have for the calorimeter. We have the stirrer, the thermometer, the lagging material is there. We have that as our calorimeter. So this is simply what we are calling the calorimeter. So for example, if we want to determine the specific heat capacity, let's say of a metal block, so and maybe in the calorimeter there is water here, then we just come and drop the metal block inside this part here. This is our calorimeter, and we'll be explaining how do we use it to determine the specific heat capacity. So I want you to note that that's the calorimeter. It is used to minimize heat loss to the surrounding when we are conducting that experiment on determination of the specific heat capacity. So this part here is highly polished to minimize heat loss, because we have seen that the polished surfaces or the shiny surfaces are poor emitters and also poor absorbers of heat. Then we have a lagging material here. We use a poor conductor of heat, like the asbestos material is a poor conductor of heat, so it is used again to minimize heat loss. Then we have lint, which is a poor conductor of heat, again to minimize heat loss. So in this calorimeter, we have seen that we have these two openings here, one for the stirrer. A stirrer is just used to stir the content, whatever is inside the calorimeter, and we have a thermometer for checking the temperature of the content. So we want to move ahead and look at how can we now use all that to determine the specific heat capacity, let's say, of a metal block. And I would like you to follow closely. After that, now we'll get into numerical calculations. So I'd like us to consider the following. In our case, I want us to determine the specific heat capacity of a metal block. So we consider the following in the determination of the specific heat capacity of a metal block. So we can have first that one, so that we can know what we want to determine. So determining the specific heat capacity of a metal block. And as I've said, I want us to consider the following. Now, in our case here, we'll consider a copper calorimeter. I've seen the calorimeter can be copper calorimeter. It can be made of aluminum also, or any appropriate metal. Aluminum is cheap, is also easily available. So in our copper calorimeter, this is our lagging material. Then here we have our lint, which is a poor conductor of heat. This is our lint. So in this experiment, we want to determine the specific heat capacity of metal block. So we consider that this copper calorimeter has water. It contains water. We have some water here at a certain temperature. This is water. Remember, we still have our stirrer here, which will now be used to stir the content. Again, we have our thermometer here. And in this experiment, we assume that the heat loss is negligible because we have tried as much as possible to minimize on heat loss. So that is what we have. So here we are having a metal block. This is our metal block. This is the metal block, which is being transferred from an oven, and then it is dropped here. It is dropped into the calorimeter. So we can have the metal block dropped into the calorimeter. So we can have it this way. This is our metal block. The metal block. So that is the consideration that we have. So here we are having our calorimeter. This is the calorimeter. And in the calorimeter, we have water. This water is at a certain temperature. And then a hot metal from an oven is transferred into the calorimeter. So we want to, when we have been given the specific heat capacity of water, we want to see what are the measurements that should be taken for us to be able to calculate the specific heat capacity of the metal block. So we want to consider what are the measurements to be recorded so that we can determine the specific heat capacity of the metal block. This is very examinable. You can be told to give the measurements that need to be taken to be able to calculate the specific heat capacity of the material. So one measurement that needs to be taken, we need first to get, or one of the measurements is the mass of the metal block. So we can first talk of the mass of the metal block. We can take it to be MB for the mass of the metal block. Here we are not using numbers, we are just using the letters to represent those numbers. But in our calculations, of course, we'll be having those numbers. So we have the mass of the metal block. We also have the initial temperature. The initial temperature of the block, that is the metal block. We can call it TMP, that is the initial temperature of the metal block. Then again, we need also to know the mass of the calorimeter with the stirrer. This is our stirrer. We also need to get the mass of the calorimeter and the star. Calorimeter with the star. We can talk of with because they are together. They are used together. The star is part of the calorimeter with the star. So for this we can use a mass of the calorimeter that way with the star. We can put it that way. Then again we need to get the mass now of the calorimeter with the star and the water, because the calorimeter contains the water. So that mass also should be recorded. So mass of the calorimeter with the star and water, with the star and also the water. So we can give it another measurement, which we can talk of the mass of the calorimeter with the star and the water. We can put ms. We can use any letter, but for our case let's use ms. Then we move on. What other reading do we need so that we can calculate the specific heat capacity of the metal block? We also need the initial temperature of water. And this initial temperature of water is the same as the initial temperature of the calorimeter, because the water is in the calorimeter. So we need to get the initial temperature, of water and the calorimeter. The initial temperature of water and the calorimeter, we can talk of it being TW for the water and the calorimeter. So that is what we have. We also need to, from this, we also need to get, we have gotten the initial temperature of the water and the calorimeter. Now, when this metal block will be put inside this calorimeter, there will be change in temperature here, because this water initially it's at this temperature and the block is at this temperature. So when they are mixed together, when the block is put in the water, they will now attain a steady temperature. So we can talk of the final temperature of the content, which is a steady temperature. We can call it the TF for the final temperature of the content. So that is what we have, and these are now the measurements that we need for us to calculate the specific heat capacity of the metal block. So we have seen one, we need to know what was the initial temperature of the metal block. Number two, what is the mass of the calorimeter with the star? Number three, what is the mass of the calorimeter with the star and the water? We have it there. Then we also need to know what is the initial temperature of the water and the calorimeter, because they are the same temperature. We get it. Then the final temperature of the content. That is now the metal block, the water, and the calorimeter. They will attain a certain temperature, that is TF. So that is what we have. So we get now into calculations and see how we can use these measurements to calculate. So calculations. So we want to get the specific heat capacity of the metal block. So before we engage the formula, we also need to know what is the mass of this water. So one of the calculations that we need to take is the mass of water. What is the mass of water? We have not calculated the mass of water. We only have the mass of the calorimeter with the star, then the mass of the calorimeter with the star and water. So from this we can be able to get the mass of water by taking the mass of the calorimeter with the star and water minus the mass of the calorimeter with the stirrer alone. So we are going to have the mass of water as this ms minus the mass of the calorimeter with the stirrer, which is mc. So that is what we have for the mass of water. Now, in this experiment, assuming that the heat loss is negligible, so note that NB, assuming then it will mean the following. So here we are assuming, because we are using the calorimeter to minimize the heat loss to the surrounding, in our calculations, the assumption is that there is negligible heat loss. When we talk of negligible heat loss, then it means that we don't have to put it into consideration. So we assume that the heat loss is negligible, and therefore note the following. So if our heat loss is negligible, then it will mean the following. It will mean that heat that is lost by the metal block will be gained by the water, and it will also be gained by the calorimeter. So we are going to say therefore that heat lost by the metal block will be equal to heat gained by the water. That is one. What else is gaining heat in this experiment? We also have our calorimeter, which is also gaining heat. But as we have seen, the calorimeter now will be able to minimize now heat loss to the surrounding. So we are going to say that heat lost by the metal block is equal to heat gained by water plus heat gained by calorimeter. Heat lost by the metal block will be equal to heat gained by water plus the heat gained by the calorimeter. Make note of that. When you have a hot spoon, a very hot spoon, you transfer it into a basin full of cold water. This spoon is losing heat. And what is gaining heat? We have the water gaining heat, and also your basin will also gain some heat. So that's what we are talking about here. And therefore, heat lost by the metal block, remember the formula for calculating the amount of heat from the specific heat capacity. We say specific heat capacity is quantity of heat all over mass multiplied by change in temperature. And therefore, quantity of heat is mass times specific heat capacity times change in temperature. So in our calculation for heat lost by the metal block, heat lost by the metal block will be given by the mass of the metal block, which is mB, multiplied by the specific heat capacity of the metal block, which is in question, specific heat capacity of the block, multiplied by the change in temperature. So what is our change in temperature for the metal block? The initial temperature of the metal block is this one. And the final temperature for the content is this one. So what is the change in temperature? Remember, this metal block is at a higher temperature than this final temperature. So we are going to have TB minus TF. So we have the change in temperature as TB minus TF. So that's what we have on that side. Is equal to heat gained by water. Again, the formula, mass of water, and the mass of water we send is ms minus mc. We can therefore say that which is equal to mass of water, mw. So we are going to take here the mass of water times the specific heat capacity of water, which should be given in this question, multiplied by the change in temperature. The initial temperature of water is here, and the final temperature is here. And you can see, since we are transferring a hot block in the water, then it means that this temperature is higher than the initial. So we'll take TF minus TW. So the change in temperature is TF minus TW. Finally, plus heat gained by the calorimeter. Again, heat gained will be given by mass of the calorimeter. There is somewhere where we have the mass of the calorimeter with the star. They are together. So we have mass of the calorimeter times the specific heat capacity of the calorimeter, which should be given. So times the specific heat capacity of the calorimeter times the change in temperature. And the temperature is changing from TW to TF. And we have seen TF is greater than TW. So the change will again be like this one, which is TF minus TW. Sorry for this. TF minus TW. And this is what we are going to have as our equation. And from this equation, it is clear that now we can be able to get the specific heat capacity of the metal block, because in this we have MB, specific heat capacity. So that's what we have. So when we want to get the specific heat capacity of the metal block, you simply come and divide both sides by MB TB minus TF. And this other side again by MB TB minus TF.